Welcome everyone. So we will continue the Bootstrap School with the second lecture on conformal Bootstrap by Shai Chester.
All right, thank you for the invitation. So this is continuing the series. The first lecture was about just basics of the Bootstrap setup and like a general outline of the algorithms, as well as some details of how to compute conformal blocks in a derivative expansion for practical use. And today's lecture is going to be making these Bootstrap algorithms more concrete by showing them actually how to implement them and to solve them using a semi-definite programming solver. So this will be a more programming heavy lecture than the previous one. And this is based on section 5 of the online notes, which you can find on the archive. So let's start with an overview. So first, we're going to start by showing how Bootstrap algorithms from the previous lecture can be written as a polynomial matrix program. And then we can rewrite that as something called a semi-definite program. And so for this, we're going to follow the original paper by the following authors. We then describe how you can use a program called SDPB developed by David Simmons-Duffin to solve such semi-definite programs. Then we're going to discuss how to compute SDPB input in practice using a Mathematica wrapper called bootstrap.m, which you can find on the online notes. So if you download the source file, you will find this Mathematica wrapper in that file, so you can follow along at home. We then show how to run SDPB on this input using Docker to get both scaling dimensions and OP coefficient bounds for the single correlator Bootstrap. And so all of this I will walk you through, and you will see that you can do it very quickly and efficiently on your laptop. We will conclude with some plots of what the results should look like with the comparison to the Ising model. Okay, so let's review the ingredients we had from the end of the previous lecture, which is what we're going to be using to bootstrap a single correlator. So the first ingredient is a list of polynomial in delta constraints. So this P is the polynomial in delta. The labels M and N refer to the fact that this polynomial was constructed by taking derivatives in Z and Z bar around the crossing symmetric point of a block minus its crossed version. The label L just refers to a block of which spin. And so recall that we include all spins up to a certain L max. This alpha mn is the functional, which is acting on this polynomial in delta. Also, this polynomial is bounded, and that for every single spin, the delta is always going to be greater than or equal to a certain delta spin b, where we can choose, for instance, unitarity as a minimal choice of bound. And also, these polynomials depend on the scaling dimension of the external operator whose 4-point function we're looking at. Because, for this lecture, as well as the previous lecture, we're just looking at a 4-point function of identical real scalars with scaling dimension delta phi.
Okay. I'm sorry, Shai, did you say that the polynomial is bounded? I didn't understand.
Well, sorry, not the polynomial, but like the value of delta is bounded.
Well done, okay.
Yeah, the value of delta, sorry, yeah, that's what I meant to say. Okay, so that's going to be the first ingredient. The second ingredient is a normalization constraint on the functional alpha, where alpha will act on the contribution to crossing of a certain operator, which we are normalizing to 1. And so for different algorithms, we normalize different operators. In one case, it might be the identity. In one case, it might be some other operator. So for generality, I just write delta norm and spin norm. And lastly, the third ingredient is some other operator. By operator, I mean the crossed block expanded in derivatives in Z and Z bar for that operator. So I'm using a shorthand. And so there's some other operator which alpha will be maximizing it. So for instance, for the OP coefficient maximization algorithm, the quantity which you're maximizing is the identity operator contribution. So in that case, you just have the crossed block expanded in derivatives in Z and Z bar for spin 0 and for scaling dimension equal to 0. That's what you get for the identity. For the scaling dimension algorithm, in contrast, the situation is a bit more trivial, where you're not really maximizing anything. So instead, you just have a vector of zeros. Okay, but these are the 3 ingredients. So it's constraints, a quantity you normalize, as well as a quantity you're maximizing. And that was the conclusion, basically, of the previous lecture. Okay, so now let's introduce the first quantity in this lecture, which is going to be the polynomial matrix program. So this will be a little bit abstract, but you'll see in a moment how this connects through the ingredients from the previous slide. So let's consider a set of mj by mj symmetric polynomial matrices, mwj of x, which have two labels. So w goes from 0 to big W, and j goes from 1 to big J. And so, as I said, this is a symmetric matrix, and the elements of this matrix we call P. Again, labeled by W and J. R and S are just the matrix labels, and because these are polynomials, they're all polynomials in this variable x. Okay, so the definition of a polynomial matrix program is that for a given B, which is a vector of length big W, the goal is to maximize the quantity B naught plus B contracted with some y over the space of all possible y's, which are also vectors of length W, such that the matrix M also contracted with this y over the label W is positive semi-definite, where that's what the symbol here means, that the matrix must be positive semi-definite for all x greater than or equal to 0, and for all values of the label j going from 1 to j. And so you can see this is why we choose two different kinds of labels, because they're used in different ways. So for the one kind of label, we actually contract with this vector y, and we're looking over the space of y's. And for the other variable, we just have a different constraint for every value of its label. And so you will see in a moment how these labels and how all these quantities I've just introduced correspond to the quantities we are familiar with from the input for the Bootstrap. So any questions just about these definitions of the polynomial matrix program? Okay, good. So now let's discuss how you write the Bootstrap algorithm as a polynomial matrix program. So firstly, this vector y, of which we're looking over the space of y's, this corresponds to our functionals alpha mn, subject to a normalization condition. So that means in particular, we had like big W's because it went from like 1 to W. And so like the length of this big W should be the size of our vector space, which recall was V big lambda from the previous lecture minus 1, where the minus 1 is because we have a normalization condition on these alphas. Also, this normalization condition makes it so that the constant in Y term, B0, as well as this constant matrix term, M0 of X, in the PMP correspond to the constant and alpha terms in our algorithm that we get after solving for one of the alpha MNs using the normalization condition. And so that's why, as you saw on this slide, there was one term which just didn't contract with the Y at all. And so that would correspond, if the Y's equal the alphas, to the fact that one of the alphas is just fixed to a number due to the normalization. Okay, so that's how we identify these Y's. The next thing we do is we describe what we mean by these matrices M. So first of all, for this lecture, we're just talking about single correlator Bootstrap. And so we actually don't need a matrix. We can just deal with a scalar quantity. So that means we can just set mj equals to 1. So we can think of these matrices M as just literally a polynomial of X. So that makes life a little bit simpler. So then the single polynomial element pwj11 of X for each of these M's corresponds to the polynomial P defined in the previous slide, which is why we use the same symbol, where we identify delta to be X plus the bound, which we were assuming delta has. And so this is such that the condition X being greater than or equal to 0 is now the same thing as delta being greater than or equal to its bound delta B. Okay, so just to reiterate, so the next entry in the dictionary is that delta is related to X, and the polynomial in the PMP is just exactly the polynomial in the stuff we're inputting into the Bootstrap algorithm. And then similarly, this label little j, which went from 1 to j, is just corresponds to the spins of the polynomial. So that is another entry in the dictionary. Finally, for the OP coefficient algorithm, the unit operator contribution that we maximize corresponds to the quantity B in the polynomial matrix program that we are also maximizing. And so similarly for the scaling dimension algorithm, in which case we're not really maximizing anything, in that case we would just set this vector B to be 0. So just to make sure this is clear, let's go back to the slide. And let's just explain again how this would translate to the Bootstrap algorithm. So B is the thing we are extremizing, which will be either a vector of zeros for the scaling dimension algorithm, or the identity for the OP coefficient algorithm. Y is basically alpha, which is the functional. W is then just the size of the functional. M just has one component for our simple case, and it's just a polynomial in X, where X is related to delta by a simple shift. And then that's it. Yeah. And then J is related to the spin. So you can see that in a very simple way, our Bootstrap algorithm is a PMP. So yeah, any questions about this mapping? Okay, good. So finally, which is a bit more non-trivial, we can now rewrite this an abstract polynomial matrix program as a semi-definite program. So where the idea of a semi-definite program is that the constraints act on matrices of numbers instead of polynomials, which is a bit easier to deal with in practice. So we use the fact that any positive semi-definite matrix of polynomials for x greater than or equal to 0 can be written as a single positive semi-definite matrix that's constant in X, so just a matrix of numbers, by using a basis of symmetric polynomials in X. So this is just a mathematical fact. You can find the proof in the papers referenced by the lecture notes, but it's not so important for the lecture at the moment. And so using this mathematical fact, we can rewrite the PMP as a semi-definite program. So I'm just calling it a dual program, where for now it's just a name. And so the definition of this program is that we are maximizing. And so also, by the way, this B and Y is the same B and Y from the previous slide. So we are maximizing B naught plus, again, B contracted with Y over the space of Ys. So that so far is exactly the same as the PMP program from the previous slide, except now there's a new ingredient, capital Y. So we're maximizing it over the space of little y and capital. This quantity P, which again, it's just the single polynomial that showed up in M from the previous slide. So P evaluated at these specific points xk, plus again, this polynomial P evaluated at points xk contracted with Y equals the trace of a new quantity we're introducing called A with this capital Y, such that capital Y is positive semi-definite. So this new quantity we introduced, A, is the thing which we use in order to write a matrix of symmetric polynomials in terms of just a matrix of numbers. And so there's just some algorithm which allows you to compute A in every case. It's like made up of Kronecker delta functions. You can find it in the lecture notes, but the specific details aren't so important for us. You just need to know that it exists. And then in particular, we evaluated at a bunch of points xk. And this allows you to relate symmetric X independent matrix Y to a linear combination of the matrices M and the Ys that showed up in the PMP. So just to say this again to make sure it's clear, the difference between the SDP and the PMP is that in the PMP, we had polynomials in X, whereas in the SDP, we just have a matrix of numbers, which is what this capital Y is. And that is something which it is easier to deal with for practical applications. Okay.
So what are these xk's?
Xk is a set of points which you evaluate the polynomial at in order to relate it to the capital Y. So the xk is related to the definition of the A, and that can be found in like the paper referenced by the lecture notes. But I mean, this is a technical.
Are you going to tell us at least how many xk's there are?
Well, in the lecture notes, I do, but
okay.
in this specific lecture, I didn't, because I didn't want to go. I mean, because like this is something which a user in practice, like, won't have to change.
Okay.
But yeah, I mean, of course, like all the numbers have to line up such that there's the same degrees of freedom in both. I guess that can be kind of your intuition about it. Okay, yeah, I'm just trying to be very brief to focus on practical things. Okay, great. So I called this the dual semi-definite program, which was basically an arbitrary name. And so the reason why I'm calling it a dual is because there's going to be a dual of the dual called the primal. So instead of a functional y that contracts with the label w in this polynomial evaluated at these points xk, where remember this polynomial is, in terms of the original Bootstrap input is just literally the derivatives of the cross blocks, or it's just a polynomial in delta. So instead of having this functional y, which is contracting with the w label, which in the original Bootstrap language was the label mn for derivatives in C and Z bar, we can also consider a primal functional, y tilde, which is contracts with all the other labels. So all the other labels being j, r, s, and k. And so recall that for our specific case, r, s is just trivial because our matrix just had one element. So r and s are both just one. Recall that j in the Bootstrap language, it basically corresponds to all the different spins. And then k is the set of points, which Slava just asked about, which is what we use to translate the original matrix of polynomials into just a numerical matrix, capital Y. And so this primal functional has all those other labels of size p, whose precise size I won't give in this lecture, but you can find in the lecture notes. And then you can define a primal program, which then naturally acts on this dual functional y tilde. So in the primal program, so now we are minimizing b naught plus this polynomial contracted with the y tilde functional over the space of all dual functionals y tilde, as well as dual capital matrices y, which are defined exactly in this equation. So the capital dual y is defined as just contracting the matrix A introduced in the previous slide with the dual functional y tilde, such that y tilde contracted with all of the other labels of p equals minus bw, and that this y tilde is positive semi-definite. So the reason why this is called the primal SDP is because it's dual to the dual SDP. And so this is just kind of an example of silly naming, where the dual SDP is actually what is most naturally related to our Bootstrap algorithm, in the sense that in the last few slides, hopefully I showed you that you can just literally rewrite the Bootstrap input in terms of the dual SDP. And the primal SDP, it's not immediately obvious how it's related to the Bootstrap input, but you can show just mathematically that this primal program, in the case where you have an optimal solution, is completely equivalent to the dual program. Okay, so it's the dual of the dual. That's why we call it prime. Okay, so now let's discuss how SDPB solves these semi-definite programs. So the way the program SDPB solves the primal and dual SDPs is that it does it at the same time. So it starts with a guess for an initial point, because remember, like the way these algorithms work is that we're looking over the space of little y's as well as big Y, where little y was a vector and big Y was a matrix of numbers. And remember also that we have y big Y and we have y tilde big Y tilde for the dual and the prime. So the idea is that you start with some initial point, which you can basically choose almost any point. And then you gradually change this initial point subject to the fact that capital Y and tilde capital Y must always be positive semi-definite. So that's something which is always exact. Whereas the other things will be approximate. So by the other things, I mean the other aspects of these programs. So like, for instance, the fact that y tilde exactly equals a contracted with y tilde. So these other things, you define deviations from these various constraints. So in the primal program, we had two constraints. So those two constraints were the fact that b is related to p and y tilde, and the fact that big capital Y tilde is related as such. So we define the deviation from both of those being correct, which is what we call delta W primal 1 and delta primal 2. And then in the dual program, which was actually a bit simpler, there was just one constraint. So that one constraint, just to go back to the dual program, is the second line. And so we define another quantity, which is like how close are we to that constraint being correct. And so then, so the idea is that we are hoping to decrease the deviation from these constraints, because in principle, we want the deviation to be 0, such these constraints are exactly true. And at the same time, we are trying to extremize the objective functions. So the objective functions were just the first line of the program. Because remember, the first line of each program, either we're minimizing one quantity in the primal version, or we're maximizing a related quantity in the dual version. And so that's the other thing we're trying to do. So we're trying to extremize these objective functions, which we just give these names dual objective and primal objective. And so SDPB is doing both of these things at the same time, step by step. Okay, so we say a point is primal feasible or dual feasible when the deviation in each SDP becomes smaller than a certain threshold value. So for instance, we can define the primal error as the maximum of either of the two primal deviations, because remember, for the primal program, there was two kinds of deviations. And then you as the user input some primal error threshold, And whenever the primal error is smaller than primal error threshold, you just declare that it is primal feasible. Similarly, for the dual program, in this case, it's simpler because you just have the one deviation, although it has various labels. So it's the maximum of all those different labels. And so that's what we call the dual error. And then you as the user will stipulate a certain dual error threshold. And then whenever the error becomes smaller than that threshold, you say that it is dual feasible. So I should note that for the scaling dimension algorithm, recall that the quantity which you're extremizing, which is a vector of zeros. And so that means that SDPB can become primal feasible, but never dual feasible, or vice versa. So what I mean to say is that if it becomes primal feasible, it will never become dual feasible. And if it becomes dual feasible, it will never become primal feasible. And so like once you found one, you know that the other will never happen.
Sorry, Shai, but this is not always true, right? It's
so what we're saying.
Depends. It's possible for it to be both dual and primal feasible.
Wait, sorry, you're saying for the scaling dimension algorithm?
Yes, like if the if you set b to 0 and primal objective happens to be, so you get primal feasible and then primal objective happens to be negative, then it implies that it cannot be dual feasible. But if it's positive, then there is no. If the primal objective is positive, it's no.
Sure, but I mean, would you say in practice that usually if it's one, it's not the other?
Yeah, that's what usually happens. Yeah.
Okay, sure. Okay. So yeah. So I guess in general that's the case, although perhaps they can be rare exceptions. So here, dual feasible means that the function alpha has been found. So that means in our practical application, that means that the delta phi and the bound is disallowed. Because remember from the previous lecture, we said that when you find the alpha, that means there's a contradiction. And so the assumption of the bound you put in must be false. While primal feasible here means that we will never find a dual feasible point, or maybe I should change never to be, it's extremely unlikely. So that means no alpha exists. And that means that in principle, the value of delta phi and delta LB that you put in could be allowed. So, I mean, it doesn't prove that it is allowed. It just means that in principle, it could. And so this is the explanation for the scaling dimension algorithm. Something else. Okay, so what I've described in this slide is the situation where you just get either primal feasible or dual feasible. But just from the abstract programming perspective, you know, what a semi-definite program really wants to do is it really wants to get both primal and dual feasible in order so that you're actually, you know, satisfying both programs. And so that's what's called an optimal solution. And this is what happens in the case of the OP coefficient extremization algorithm. So, because remember in that case, the value of B is non-zero. And so then we expect that, you know, these Y's and capital Y's should become both primal and dual feasible, which you can show implies that their difference is non-negative. So this is something you can just derive. So the difference between the primal objective and the dual objective, it ends up being the same as the trace of big Y and big tilde Y together, which you can show is always strictly positive. Then you can define something called the duality gap, which is just the difference between the primal objective and the dual objective, normalized in this nice way. And then you will find that the duality gap will gradually decrease until it's smaller than some user-specified duality gap threshold, at which point you declare that the objective functions are approximately equal, which implies that big Y tilde contracted with big Y is approximately 0. And then you say that this choice of the Y's is an optimal solution. And so for the OP coefficient algorithm, you will then find that this primal objective, which is then roughly the same as the dual objective, is up to assign the upper or lower bound on the OP coefficient squared. So just to reiterate, you in general will only find an optimal solution when you are doing the OP coefficient algorithm. So you don't find it for the scaling dimension algorithm. In the scaling dimension algorithm, your goal was just to see if a functional existed at all. And so in that case, you just expect to find that either it's dual feasible or primal feasible. It's only in the OP coefficient algorithm that you're kind of using semi-definite programming to its fullest extent, where you find that it's dual feasible. You also find that it's primal feasible. Even more than that, you then find an optimal solution. And then that optimal solution indeed is your bound on the OP coefficient squared. And so that's also why in general, extremizing OP coefficients usually will take longer than just seeing if a functional is allowed or disallowed. Okay, so this was a bit abstract, and so hopefully people were following, but even if you weren't, soon there'll be a practical demonstration, and then everything will hopefully become more clear. let's talk about the explicit inputs for SDPB. So in the previous lecture, we discussed how to compute polynomials of x, where remember x we just define as the difference between delta and its bound. And so we discussed how to compute these polynomials from derivatives in z and z bar around the crossing symmetric point of this crossed block, where we got the polynomial starting from the block itself, which was not a polynomial in delta, by factoring out some positive product, where in particular the positive product was of a bunch of poles, as well as some factor, which was this crossing symmetric r to the power delta. And so we define this positive quantity as chi of x. So now I'm going to describe in detail how exactly you can use these polynomials of x, as well as this positive quantity of x, to construct the three inputs that are needed to actually make our SDP. So this was the thing we discussed in the very first slide of this lecture. So in particular, just to reiterate, the first input, which is the polynomial constraints themselves, consists of a table of these polynomials labeled by mn for each derivative in z and z bar, as well as L for each spin as a function of x. So we have a table, one for every even spin up to some spin max, each of which is a table of z and z bar derivatives such that n plus n is odd and n plus n is less than or equal to big lambda. Where the fact that it has to be odd just has to do with how this function is constructed. So if it was even, it would just be 0. And then something we just do for numerical stability is that after we have constructed this polynomial, we multiply this table by this positive function chi of x evaluated at some specific points. Sorry, that's a typo. It just shouldn't be at unitary. It's evaluated at some specific points such that the blocks have their natural size. Because like if we didn't multiply it by it, then this polynomial would have like, I don't know, incredibly tiny or incredibly huge numbers, and that can lead to issues numerically. So the second thing we're going to construct is an objective function, which I call obj, that the functional alpha will maximize. So unlike the polynomial constraints, this quantity is not a function of x. So it's constant in x, but it is still a table of derivatives in z and z bar, like similar to the polynomial. So in particular for the scaling dimension algorithm, this objective quantity is just a vector of zeros, as we've been reiterating. Whereas for the OP coefficient algorithm, this objective function that we're extremizing is the unit operator, expanded in derivatives in z and z bar. Finally, the third quantity is the thing which we are normalizing the functional with. And so for the scaling dimension algorithm, the quantity we normalize, recall, is just the identity contribution. Whereas the OP coefficient algorithm, the quantity we are normalizing is the specific operator whose OP coefficient we want to normalize, as discussed in the previous lecture. Okay, so these are the three inputs. And so now, to make this a little bit more concrete, I will actually show you how to construct these inputs using the Mathematica wrapper, which is given in the lecture notes. And so I'm just going to be using one on my computer. So I'm just going to share my screen. It's going to be a moment so you can see this. Okay, here, great. So here I'm sharing my screen. I hope the font is big enough. Maybe I'll make it a little bigger. Great. Okay, so this is the Mathematica wrapper, which can be found in the source file for the lecture notes. This is, I think, originally was made by Alessandro Vici many years ago. It can also be found on the GitHub for SDPB. And so the beginning of this wrapper, you could just think of as a black box. And so I'm not going to go into it in so much detail. Like it's just a black box that is going to take your input and like put it into a convenient form for SDPB. The more interesting part is the functional or the function which you will be modifying in order to adapt to different Bootstrap uses. And so that's the thing I want to go through just a little bit more in detail, because this is, I guess, the more interesting part. So the first example of input we're going to make is if you were just trying to see for a single correlator if a point is allowed or disallowed. And so this is what I call the scaling dimension algorithm, where I've called it icing because in practice, we're then going to relate these bounds to the icing model. So as you see, this function is very simple. So the first thing we do is that we just load in the derivatives in z and z bar of the blocks. That's what this function f is doing. And so these blocks you could have computed beforehand using scalar blocks as described in the previous lecture. And so you can just have a table pre-computed, and then you just load them in. The second quantity is the list of poles. And so this has to do with the quantity chi of x, which as mentioned was the positive quantity which you took away from the blocks in order to turn them into a polynomial in delta. So this is just a convenient list of poles. So here, this function v is where we define our list of polynomial constraints. So as mentioned just a moment ago in the slides, the polynomial constraints, first of all, you have a different constraint, one for every spin. And that's why this table is going over spins, over all even spins in the choice of spins you have. And then each entry is itself a table of derivatives in z and z bar. But that's exactly what f is, right? Because as I just mentioned, what f is doing is that it is calling derivatives in z and z bar. So it's a table, each of which, it's a table in spins, each of which is a table of derivatives in z and z bar called as such. And so there's this, so the way this wrapper works is that it constructs a quantity called positive matrix with prefactor. In this case, the matrix is just one entry. So it's a bit trivial. So that's why you just see like asterisk, asterisk, and then one thing, because we're just doing a single correlator bootstrap. And then the prefactor is what I mentioned is the factor chi of x, where you're just putting that in order so that the size of this constraint is roughly the size of what the blocks originally would have been. And this just helps with numerical stability. And so that's what the CD prefactor is. It's just a combination of all the poles as well as this factor r to the delta evaluated at some specific values of x. So just a number. Finally,
but how is this a number? It depends on x. It's not a number. It's a function of x.
Well, it doesn't depend on x after it's processed. So the way it works is that within this function you enter it and it depends on x. But the way the positive matrix with prefactor is defined is such that when you process it using the black box in the beginning of the notebook, it will be turned into just a number. So yeah, okay, but thanks for asking. Yeah, because it's important that it is just a number, because the important thing is that we want to be putting in polynomials in x. So we can't just multiply back by the poles, otherwise we wouldn't have polynomials in. Okay.
And so it's something of the order e to the delta times a some small number to the power delta. You're saying it's.
Well, yeah, I mean, I forget if it's really big or really small. I mean, it's one or the other, because I mean, the idea is that it's like 0.17 roughly, which is what r at the cross symmetric point is, to the power of delta, and then it's divided by all these poles, and like there could be many poles, and then you're gonna be evaluating this, for some specific value of delta, i.e. x. And then, I mean, it's a conveniently chosen point such that on the whole, your polynomial delta will be like of order 1, because you don't want it to be like, some huge quantity. Otherwise, that'll hurt the numerical stability. Another thing we do, so this is getting a little bit technical, but it's actually important to some extent, is that, so this is kind of an annoying technical thing, but the way scalar blocks works is that when it replaces the poles in your block expansion, it uses a list of poles that in a sense is like not the natural list of poles. So like if you're doing a single correlator bootstrap, there's certain poles that should appear, whereas the poles it replaces it with are the poles that would have appeared in a mixed correlator bootstrap, which is a more general list. And so that's okay, because in principle, when you're replacing poles, you could have replaced the poles by any poles, because like it's just a statement that you're replacing, a function of like 1 over a number minus x by a sum of some other poles. And so it doesn't really matter which poles you replace it with. But one kind of annoying feature of the specific poles we choose is that for the case where spin is bigger than 0 and for the single correlator bootstrap, it makes it so that you get a polynomial in x which doesn't have a constant term. So the polynomial starts with x, because you basically kind of like put in a pole which made it so that when x is 0, the polynomial is 0. And so this can lead to some numerical instability problems. And this is why in practice what we do is that we take the polynomials in x, we divide them by this x, and then we put that extra x into the prefactor, which is okay because this x is positive. And the only thing which is important is that we have a positive quantity multiplying our polynomial. So in general, we're always allowed to multiply by any positive quantity. And so this way, we get rid of this potential numerical instability of having a polynomial without a constant. Okay, so that's what this function v is doing. It's creating the polynomial constraints. Here, I allow for the possibility where you might want to insert a gap. And then in the case where you're inserting a gap, remember, as we discussed in the previous slide, that means you just put an operator at a fixed value of delta below your gap for that specific spin. So for instance, here in this case, I'm assuming that we are putting a gap on the spin 0 sector. And then I'm just putting one of these polynomial matrix constraints. Although in this case, it's not even a polynomial, because x is just fixed to be the value of the operator you're inserting at that specific point. So here you see that the way this thing looks, it looks exactly like the v, except that x is fixed to a specific number. And then instead of having, instead of like putting it in with like the CB prefactor in the first argument of positive matrix with prefactor, instead we just explicitly put in what that thing is. So it just literally is 0.17 to the power delta divided by the product of all these poles. Okay, and so then poles is just the previous two things I described. So it's a list of polynomial matrix constraints. And then optionally, you can also insert an operator, where here I've chosen to not insert it. So then the second ingredient we described is there's the quantity which we want to normalize. And so for the scaling dimension algorithm, the quantity which we are normalizing is just the unit operator contribution. So because the unit operator is special and that its spin is 0 and its scaling dimension is 0, so instead of loading in from scalar blocks and then just setting x equal to 0 and spin equals to 0, you could just do something much simpler. Because this is just an exact function, you might as well just take its derivatives in z and z bar exactly. And so that's what this function does for you. So this function is just derivatives in z and z bar of the trivial unit operator block, where the unit operator block is 1, but then it's multiplied by u to the delta phi. So this is just basically derivatives of u to the delta phi around the value z and z bar equals 1/2.
Yeah, that's actually another question I had. So the other blocks, have they already been multiplied by u to the delta phi at this point, and where did this happen?
Okay, good question. So scalar blocks does not include that. So scalar blocks just gives you the derivatives of the blocks in terms of z and z bar. So the way you get the power of u to the delta phi, yeah. So thanks for reminding me. I forgot to point that out. That's part of what's being done in this function f. So what this function f does is that it loads in scalar blocks, and then this add delta phi function then basically takes derivatives of like one quantity in terms of z and z bar, and then outputs that quantity multiplied by u to the delta phi with derivatives of z and z bar on the total thing. That's being done in the function f. Yeah, thanks for reminding me about that. Okay, so unit operator is just doing the same thing, but for the trivial case of the unit operator. And then we just define the normalization as this unit operator. Finally, because we are doing the scaling dimension algorithm, the quantity we're extremizing is just a vector of zeros, but it's important that that vector of zeros have the right length. So it should have the exact same length as norm, which is why we just take 0 multiplied by norm. So finally, we have our three quantities. We have the list of polynomial constraints. We have the quantity we're normalizing, as well as the quality we're extremizing. And so then we plug it in to this function called write bootstrap SDP. And you could just think of that as a black box, which takes these three inputs and massages them into a form which can then be inputted into SDPB. So that is what happens for the scaling dimension algorithm. And then I will just briefly say what happens for the OP coefficient algorithm, which is a very simple modification. So here I call it icing CT, because this program I'm choosing specifically to extremize the OP coefficient of the stress tensor, which is kind of the natural sort of thing you might want to extremize. Most of this function looks exactly the same as the previous one. So for instance, the list of polynomial constraints is exactly the same. It doesn't change at all. Similarly, is an option of inserting a gap with an operator, but we want not do that anyways, so that's just commented out. So the way this program becomes different is that, first of all, the quantity we're normalizing is no longer the unit operator. Instead, we're normalizing the stress tensor operator. And so here we see something that looks exactly like one of these polynomial matrix constraints, which showed up in V, except we're specializing specifically to spin 2. So that's why we have this function f evaluated at 2. So this is loading in derivative of a spin 2 block, multiplying by u to the delta phi, and then taking derivatives. And then here we are normalizing it such that we are basically adding back in the what's it called, the 0.17 to the delta, as well as the product of poles. So that's what's going on here. Where in particular, I'm also including a 4 to the delta because that's one of the more natural normalizations. Again, remember the thing we normalize is always just like a number. It's not a polynomial in X. And so we're doing specifically the stress tensor. We're doing it in 3 dimensions. And that's why I'm setting delta to equal 3. Remember, delta is related to X by some shift. Finally, and this is related to the fact that we were dividing by X before. So again, there's this annoying thing where like the way scalar blocks was defined is such that the polynomial you get doesn't have a constant term. And so we're basically plugging in X equals 0. because x equals 0 corresponds to delta equals 3, which is what you want for the stress tensor. And so you would have this instability where if you just literally plugged in x equal to 0, you would get 0, but then you'd want to divide by 0. So you get 0 over 0, and it would cause headaches. So to avoid that, we divide by x here, and then multiply by x back here. And so here, when you multiply by x, it's just going to cancel a trivial pole 1 over x. And so such that you just get a number. And then here, it basically makes it so you have a constant term. So that after you plug in x, you just get a nice number without any 0 over 0s. Finally, one last ingredient we put in is that, remember from the previous lecture, that when you are relating CT to the stress tensor OP coefficient, there's this factor of delta phi squared. So of course, I mean, in principle, we could have just extremized the OP coefficient, and then after the fact, we could have put in the value of delta phi. But just for convenience and to make the answer look a bit simpler, I've just put in this factor already here. And so that means the output you're going to get is going to be much easier to immediately interpret in terms of CT. Okay, great. So this is the two functions, one for extremizing the stress tensor OP coefficient, one for creating the input for the scaling dimension algorithm to see if a point is allowed or disallowed. And so now let's actually run these programs. And so you'll see that it just takes a split second to run. So here I'm just going to run them. The first thing I'm running is I'm doing this. Okay, so let me explain all these parameters. So first of all, I'm looking for spins from 0 to 15, which in practice means 14, because I'm just looking at even spins. Then I'm choosing Rmax, which remember is the order in which we expand the block. I'm choosing Rmax 40, which is a conservative choice. Kappa is the parameter which says how you replace poles, which in a sense says how accurate the blocks are. So I'm choosing kappa equals 10, which is also a conservative choice. And then the most important parameter is the value of lambda. So the way this code works is that the way you enter lambda is in terms of a parameter called nmax, which is just 2 nmax minus 1 equals lambda. So I'm putting in nmax equals 6, which corresponds to lambda equals 13. So that's the important parameter. This is the parameter which says how accurate the bootstrap is. And then these other numbers, so the third number you can ignore. The first two numbers, the first one is the value of delta phi. So I'm going to choose 0.52 for all three of these runs. And then the second number is the value of the bound we're putting on the lowest dimension spin 0 operator. So the first time I'm going to run this, I'm going to call it test 14. And this is going to be where I put the bound on the lowest dimension scalar to be 1.4, whereas for all other spin operators, I just use unitarity. And so if I can find a functional, that means this assumption was disallowed. And so that means the specific point delta phi equals 0.52 and the lowest dimension scalar being 1.4 is not allowed. Okay, so let me create this input. And then for comparison, I'm also going to do an identical input, except now I let the bound be 1.5. And the reason is that, as you're going to see in a moment, one of these points is allowed, one of these points is disallowed. And so you can see in each case how you get a slightly different result from running the algorithm. And then finally, I'll also create the input for doing a bound on the OP coefficient for the stress tensor. As you see, it also takes a second. Okay, so let me go back to Zoom. And so I will, I need to share my Zoom again. How do I open the Zoom thing? Sorry, wait a moment. Sorry, technical difficulty here. Trying to like go back to where I can share screen.
We are still seeing your screen, your Bootstrap.
Oh, okay, great. Okay, I got it. Okay, great. Okay, so now I'm going to share screen again with my slides. Okay, great. So I just described how to create the explicit input. So now let me describe how SDPB is now going to process this input. So for the scaling dimension algorithm, we want SDPB to end the moment it becomes either dual primal or dual feasible. Because as mentioned, in most cases, this implies that then it can't be the other. And so i.e. this will say, like, does the function alpha exist or does it not exist? So we can make this process faster by turning on the feasibility parameters, which I'll describe in a moment. So that means we have the parameter list. So there's a list of parameters you have to put in when running SDPB. There's actually more parameters than I'm showing here, But the ones I don't show, you can usually just leave to their default parameters. So like the ones I'm showing are the ones you might conceivably want to change. And these are also the ones I just described. So remember, so you have duality gap threshold, you have primal error threshold, dual error threshold. What I call the feasibility parameters are these 4 parameters, which I've all turned on by setting them equal to 1. And so the first 2 things just say that I'm telling SDPB to terminate if it finds a primal feasible point or a dual feasible point, which is something I would only do for the scaling dimension algorithm, because if it terminates at this point, that means I will never be able to find an optimal point. But that's okay, because for the scaling dimension algorithm, I don't expect to find an optimal point. These other 2 parameters are a bit more interesting. So basically, the way SDPB is written, so you're changing the y's step by step. And if a certain step is like very big in a certain way, which is called like a jump, then it basically implies that you will never be able to find either a dual point or you'll never be able to find a point. And so this just makes it faster, because that means instead of having to like run many steps until you literally found primal dual or primal feasible or dual feasible, instead when these jumps occur, the way SVB is written, the code just knows that you never will find a primal point or a dual feasible point, and so you can just terminate immediately. Finally, there is the precision of SDPB, which, as mentioned in the previous lecture, you have to set to a very high value. So this is kind of one of the big barriers right now to improving SDPB, is that you need to choose precision. And then finally, there's the number of processors I'm going to use to run SDPB. So one of the nice advantages of SDPB is that it's a parallelizable program. So that means you can use multiple cores at once. And so even on my humble laptop, I have 4 cores, and so I can use all 4. So now let me describe the parameters we're going to use for the OP coefficient algorithm. Most of the parameters are pretty similar, except we turn off all the feasibility parameters. Because remember that for the OP coefficient algorithm, we don't want to find just a primal point or just a dual point. We want it to become both primal and dual feasible. And furthermore, we actually want to find an optimal point. And so we don't want SVP to end early. Also, because we're trying to find an optimal point, usually you need a bit more precision. And so that's why I'm using 200 more digits of precision. And those are the main changes. And that's kind of a general story, that you should always use a bit more precision when doing OP coefficient maximization versus just finding an alpha for the scaling dimension algorithm. Okay, so now let me demonstrate how we will actually run this with SDPB. Okay, so I'm going to stop my share, and then I'm going to share screen yet again. This time I've become a little better at it with the terminal. Do you see the terminal here? For some reason, I'm not finding the terminal. Okay, let me try to share with Finder. No, but this is just showing Finder, right? Sorry. Here's the terminal. Great. Okay, great. So now I'm going to my terminal, and I'm going to use Docker, just as we described in the previous lecture when we were creating scalar blocks. Now, instead, I'm going to use Docker to process. So there's going to be 2 steps. First, I need to process the files I created using the Mathematica wrapper into a form where they can be run by SDPB, and then I'm going to run them with SDPB. So it's a 2-step process. So the first step is very quick. So here in Docker, I'm going to the command where I turn these things into the right format. So this is called PVM to SDP. So let's just go through again how Docker works. So the way it works is that you're sharing a certain notebook on your laptop, which in my case is users Shai Chester desktop Bootstrap. So I'm sharing it with this cloud, which is where Walter Laundry conveniently put all these codes. So in particular, he has a code called PVM to SDP, which is being invoked right here. I'm running it just with 1 core because it's very quick anyways. With precision 1000, which is overkill, but it's very quick anyways. And then what I'm doing is that I'm taking input 14, which was this Mathematica file I created with Mathematica, and I'm just turning it into the right kind of input for SDPB. Okay, so let's do that for the 3 codes we created. And as you see, each one basically takes a second.
I actually don't see anything happening.
Yeah.
Sorry, can you see, is my screen shared?
It's shared, but nothing is happening.
Yeah, we see a terminal. It's like on the first tab, and it says the last line is like VI and some.
Okay, let me try sharing again. Okay, so can you see things happening?
Yeah, now it's better. Yeah.
Great. Okay, great. Okay, great. So yeah, I mean, okay, so all I'm doing is I'm creating this input by running pvm test dp. So I first do it for test 14, then I do it for test 15, which was the other scaling dimension point, and then finally I'm going to do it for the OP coefficient case, which was I call test CT. Okay, so that's the first thing I do, and then what this will do is that it just creates a file on your desktop in the folder you chose. So in my case, that's what I call Bootstrap. And it creates a folder, which just has the exact same name. So
yes, if you're showing us the if you're showing us the Finder, we cannot see it. We can only see the window that you shared.
I understand. Yeah,
okay.
but it's not so. I don't think I need to show that. I mean, it's just creating a file in my folder which has the name of this input I'm going to put into SDPB. So it's just a file. Nothing so interesting. Okay. So
what is the point of first generating this XML and then transforming it to SD? Why can't we just generate directly this?
Well, I think it's just more quick this way. So like, I mean, Mathematica is much slower than C++. And so in principle, I guess you could have chosen Mathematica just to write input in exactly the way that SDPB likes, but that could take a really long time, especially if you're doing some huge Bootstrap. And so instead, this pvm test dp just does it, using C++ in like a super optimized way, which is incredibly efficient. Yeah. So yeah, I mean, it's a technical detail. That's why I didn't even mention it in the lecture notes, because I don't think it's so.
So XML files are smaller than these other files, these directories.
Well, I think in practice it might actually be bigger, because I think the thing you produce is bigger than the Mathematica wrapper file. Although I don't remember offhand. Anyway, okay, so that was the first step. We just translated into a slightly different form. So now let's do the more interesting step, which is where we are actually going to run SDPB on this thing we just created. Okay, so let me find it. So here we are running. I want for test 14. Great. Okay. So let's first show the example for test 14. Oh, sorry. Oh no, sorry. I just ran pvm test db again. Sorry. Here. Great. So now I'm running SDPB on this input file I just made, and as you see, it goes incredibly quickly. So it ended before I could even explain it, but luckily I have it all saved on the screen. So let's just see exactly what happened. So first of all, the objective value for the dual feasible program is just 0, because remember, for the scaling dimension algorithm, well, there is nothing. It's just a vector of zeros. So that's expected to be 0. The only thing which is non-zero is the primal objective. And so in general, if a functional cannot be found, you're going to find that the primal objective is going to get bigger and bigger and bigger, which is what happened. So it started at like 10 to the 27, and then it grew to 10 to the 29. In principle, it would have kept growing. Except we turned on this parameter called primal feasible jump. And so what happened basically is that the program did a really big step in a way that it knew that it would never be able to find a functional. And so that's why the program just terminates. And this is how we know that this point is not disallowed. So remember, the two options is that either you find a functional, in which case you know a point isn't allowed, or you don't find a functional, in which case you just don't know anything. So in this case, we don't know anything. But there's the possibility that this point could be allowed. Yeah.
Sorry, I just wanted to point out that here it's actually, so this, the summary at the bottom, it says primal error is like 10 to the minus 208, which is not visible in this list of steps. So it actually found, what happened is that it found the primal solution, and you can see that the primal objective for this primal solution is negative. So it proves that there is no functional.
Sure. Yeah. Exactly. Okay. Yeah. So this is as you were saying. Yeah. So it's fine. So it's basically saying you can't find like a dual feasible thing, which is what we care about from the perspective of knowing if a functional is allowed or not.
But for example, could it happen, Peter, that there would be this primal feasible jump, which means that primal error is very small, 0, but primal objective, for example, is still positive? Could this happen in principle?
Well, I haven't seen this happening, but I also don't know like of a one sentence proof that this cannot happen. So maybe if one studies the particular programs that we're looking at, one can prove that this is always the case, but I don't know simple.
Yeah, I can say in my experience, it never happens unless there's some problem with your code and then you have to fix things. But like, when things are working, it doesn't happen. Okay, great. Okay, so we just checked that the value of delta phi equals 0.52 and the bound on the lowest dimension scalar of 1.4 has the possibility of being allowed. Now let's check the analogous thing when the bound is 1.5. So we're just going to run SDPB on that other input file we just made. Okay, so it should be running. For some reason, it doesn't seem to be running. Okay, let me try running this again. Oh, good. Okay, great. So now it's running. And so as you see, in contrast to the previous run, where the value of P objective was getting bigger and bigger, and then it had this primal feasible jump, now it's getting smaller and smaller. And so that's good, because that means that it's getting closer and closer to finding a dual feasible point. And indeed, it finds it. So like the way that it knew that it found it is that basically, I chose like a certain cutoff of like when I say that I found a dual feasible point, and this value got small enough such that it was smaller than my cutoff. And so that's why I declare that I found a dual feasible solution. So this means that I found a functional, which means that this point is disallowed. And so like just the takeaway between these two cases is just that in the case where a point is allowed, you will see the P objective getting bigger. In the case where it's disallowed, you'll see the P objective getting smaller. Now, for this simple case of a single correlator, this was incredibly quick because I was also doing it just for like lambda equals 13. And so in the case where you're doing like a huge value of lambda, there might be some fluctuations. So it might be the case that maybe P objective would first go up and then it would go down. But like it should eventually stabilize, and then it should eventually either go just down or just up. And so if that doesn't happen, like then that means you have some problem with your input. But in every reasonable case, this is what should happen. Great. So we found an allowed point, we found a disallowed point. And for my last trick, I will show you how to extremize the value of the stress tensor OPE coefficient. So here I'm now applying SDPB to the third input, which was input CT, which was the stress tensor OPE coefficient code. So now I'm running this. And so this code will take a little bit longer, although not that much longer. But the reason why it takes longer is that recall that for the OP coefficient algorithm, you first need to find both primal and dual feasible. And then afterwards, you want to furthermore find an optimal point. So what's going to happen here is that you see that now both the P objective and the D objective are both non-zero because you're actually extremizing something. So it's not the case that the B vector is a zero. So they're both non-zero. So what always happens is that first the P objective will get smaller and smaller and smaller. While meanwhile, it looks like the D objective is getting bigger, which would be a problem, right? Because eventually you want them to be exactly the same thing. But you shouldn't panic, because what always happens in practice is that after a certain amount of fluctuation, the P objective will become small. So you see it's still fluctuating. And then after the P objective becomes small, then the D objective will also become small, and then eventually they're going to join at some value. And so that's what's happening. So you see the P objective was fluctuating a little bit. Now it's just becoming, uniformly small. The D objective is also becoming uniformly small, and they are happily joining together to find our optimal solution. So, okay, great. So I think we're just about to finish. And as you see, they're both becoming the same negative number, which is around -1. So first of all, the fact that you're getting a negative number, this is to be expected, because you should remember that from the OP coefficient algorithm, there's two choices. Either you get an upper bound or a lower bound. But if you're not inserting a gap, you can only get a lower bound. And the way the lower bound works is that that lower bound is minus whatever your objective functional is. So that's why we expect the objective functional is minus, because we multiply by -1, and then that is our bound. So it's good that we got a minus here. And so what we've just learned is that the bound on the stress tensor OP coefficient multiplied by delta phi squared, which I just put into the code, is slightly bigger than 1. And then recall from the lectures that CT was related to the inverse of the stress tensor OP coefficient, as well as with that factor of delta phi squared. And so you basically want to take the inverse of this number. And so that means we're going to get, instead of an upper bound on the stress tensor OP coefficient, we're going to get a lower bound on the value of CT, which is just the inverse of like 1.06. So we're going to get something which is slightly smaller than 1. And that's exactly the answer we expect, as you're going to see in a moment. Great. So while I go back to the lectures, any questions about how this practical demonstration worked for running SDPB?
Looks great.
Okay. Okay, good. Okay, so no questions. That's good. So let me just share back my lectures. Here it is. Great. Okay, so now let's show what the answer would be if you just ran the algorithms I just showed you many times, which is exactly what you can do at home. Because as you saw, each run took like 10 seconds. So let's first describe the results for the scaling dimension algorithm. So in this plot, the x-axis is the value of the delta phi, which in this case I'm calling sigma because I'm defining sigma as the lowest dimension Z2 odd operator. The y-axis is the bound which we were putting on the lowest dimension scalar, which I call delta epsilon. And then I'm showing I'm showing four things. So firstly, I'm showing bounds with more or less values of lambda. So in the demonstration, I was using lambda equals 11, as well as, or I think I was actually using lambda equals 13. Oh, no, sorry, I was using lambda equals 11, as well as these other parameters. So that was slightly less accurate. But just for comparison, because it looks a bit nicer, I also show the results you would get from using lambda equals 19. And I should note that you can actually also do lambda equals 19 on your laptop. It also doesn't take that long. It's just like twice the time, but it's still also reasonable. So that's the comparison between the dashed bounds and the solid lines. The second thing to note is that I've showed you one plot, which is where there was no assumptions. So all I did is that I was putting in different values of delta sigma, and then I was looking at different possible bounds for delta epsilon. And that's what gives you this upper bound here, which has a kink right at this red point, which is where Monte Carlo tells us the Ising model should be. But then I'm also showing you a different kind of bound, which is given by these brown lines. And so these brown lines is where I put a gap on the spin 0 sector, and then I insert an operator below. Because remember when I was showing you that input, I showed you how there's like an option of inserting an operator. And so if I were just to have run the Bootstrap with that option, then I would get both upper and lower bounds, at least within this regime. And then it gives us this peninsular shape, of which its dagger is very near where the Ising model is. And of course, as you can probably expect, if you were to go to even higher values of lambda, eventually the point of this dagger would be exactly where the Ising model sits. So this is kind of, historically, like these were the plots that people first made, which is got people first excited about the Bootstrap, because you could see that you were finding this very interesting kink and dagger right where the Ising model is. And these are things you can really just do now on your laptop in like under an hour. So you just have to run a bunch of points in this vicinity and you will see exactly this kink. So any questions about this plot? Well, one other interesting thing I should note about this plot, which I think is actually something which, as far as I know, people never pointed it out. Maybe it was obvious to them, which is that you'll notice that as you change lambda, most of the plot is changing. And the only point that doesn't change is where the red dot is. So, it's almost kind of like a hint to like that point is like where something interesting was going on, because that's the only point that didn't change. And so I don't know if this is like a general principle, and like I don't know if this would happen in all cases, but it certainly happens in the Ising model, and it also happens in the ON model. And so this might even be a help when you're like, I don't know, searching for some putative CFT. If you notice there's a certain point which isn't changing as you change the value of lambda, then like that could be a smoking gun, but there's an actual CFT that's living there. Okay.
But of course, eventually the whole plot will converge whatever you do. So
sure, exactly. Yeah, I'm just saying, like, I don't know, like imagine you're doing some Bootstrap with like 100 correlation functions. It's really slow. It's hard to go to high lambda. Like if you want to know that at least there's something interesting in your plot, the fact that there's like one point which isn't changing, whereas every other point is changing, could show you on the right track.
I see.
Yeah. Okay, great. So secondly, I'm going to show you the result of the OP coefficient plot. So here again, the x-axis is delta phi, which I call here delta sigma. Again, I'm running for points right near 0.52. So in the demonstration, I just showed you 0.52, but I also do points to the left and to the right. And the y-axis is the value of CT normalized by the value of CT for the free theory. And so that's why at the free theory, you would just expect to get 1. Whereas what we find here is that we are finding a minimum just below 1. And so this is consistent with what I showed you in the demonstration. Because remember in the demonstration, I was getting the lower bound on the OP coefficient and it was like something like 1.06. But then I have to take the inverse of that to get CT, and then I get a lower bound. And that's exactly what you see here, which is something around 0.95. So again, the gray versus the black is just increasing the value of lambda. This is a situation where increasing the value of lambda like really actually makes the plot look much nicer. Because like at lambda equals 11, you can like barely see a minimum and it's, kind of crappy. Whereas the moment you go to lambda equals 19, there's like a very clear minimum right near the value of the x-axis where you know the icing model is. So you might ask why I'm just showing a vertical line here instead of showing, a dot. And the reason is that as far as I know, there are no other independent accurate predictions for the value of CT. So in a sense, it makes this more interesting because it's like, the bootstrap you could say is, the only way to really accurately know what CT is. Okay, great. So that concludes this lecture. And hopefully people will join in next week. So any questions?
Thank you very much, Shai. Questions?
I mean, I have a question. So in the S matrix bootstrap, or maybe not so much recently, but in the beginning, people cared a lot about this primal approach and they were looking at how the S matrices look. Why did we never care at all about the primal approach?
Well, no, sorry, you're saying
what the primal functional tells.
Well, no, look,
yeah, in the numerical bootstrap.
Look, we care about both because the way SDPB solves a semi-definite program is that it's simultaneously looking at both the primal and dual problem at the exact same time. So we certainly care about both. It's just the case that it's the dual program which is more directly related to like the bootstrap algorithm. So that's why it's kind of like, that's the thing we care about more because it has more, physical interpretation. But like in terms of the programming implementation, of course we care about both because like they're both being optimized at the same time.
I mean, in the sense that the primal problem somehow constructs approximate solutions and not just, of course, you cannot take them rigorously, but maybe they have some insight into the structure of correlators in general, even deep inside the allowed region.
Yeah, okay.
Because
but when we find an optimal point, the primal and dual problem are exactly the same. So like they're not telling us anything different. Like it's like, remember, like there's two algorithms. Like one algorithm is just like, do we have a functional or not? And for that, we just care if we have a functional. The second algorithm is like, okay, what is this actual specific functional? And then if we find one, then it's the same functional from both the dual and the primal problem, by definition.
I think there's a little bit of confusion here because there are two primal problems. One primal problem that you can get if you take the polynomial matrix problem and you take kind of dual of that. And this, I think, is what the question is about. And another one is the one that SDPB uses, which is you first convert this polynomial matrix problem into SDP, and then you take the duality, which is a different problem from doing this before the conversion. And before the conversion, the primal form problem has a clear interpretation that it's trying to find solutions to crossing, essentially. And after the conversion, the interpretation is not clear. Physically. So maybe there is some relation, but I don't think anybody figured it out explicitly. It's not, at least it's not published, I think.
That's what I meant. Thanks, Peter.
But also, if I may say something, it's not true that the primal problem has not been used in the numerical bootstrap. In fact, these CT plots, they were first produced with a linear programming algorithm, which was a primal linear programming algorithm that was in our semi-minimization paper that was based on the primal algorithm. It was not SDPB, it was another algorithm, it was a primal algorithm. So at every step of minimizing C, we were moving from one solution to crossing to another solution to crossing. And there was not an exact solution to crossing, but it was a solution to crossing to a given order in the ZZ bar expansion around the crossing symmetric point. So it was a primal algorithm. So when we were doing linear programming, we were using both primal and dual solutions. There was really not that much difference. While when people moved to semi-definite programming, then indeed this difference appeared that Petr has just mentioned, that now there are two primal problems. So one has to be a bit careful. And as to the interpretation of the dual problem, I think there is something in an appendix of a paper by Balt about interpretation. Maybe Balt wants to comment on this.
The appendix is one thing. I think also it is just clear that because the spectrum extraction tool by David Simmons-Duffin uses the primal matrix to read off the OP coefficients. So the primal SDPB problem does in some way, well, what can I say? I want to say that it does know about the solution to crossing symmetry, but it's really a combination at the moment of primal and dual that you need to extract the solution to crossing symmetry.
I mean, but from what I understand, that like David's code, it's assuming that you found like an optimal point. So it's like what he did is that he would like extremize CT, you know, say throughout an island, and you get an optimal point. And at the optimal point, the primal problem, the dual problem are basically the same. So like, you know, it's not so surprising that they would like, you know, both directly apply it to the, you know, the crossing equations.
Well, I'm not sure if they're the same. If you can give me a matrix X, can you reproduce the matrix Y? Right. Or vice versa. That would be saying that, roughly speaking, that would be saying that they're really the same. But I think both matrices contain the full information about the problem.
You're saying you need both matrices to really know everything. Like you can't automatically get one from the other if you have one and if you assume you have found an optimal point.
Might be hard. Are you saying, so you're asking about the solution to crossing symmetry that you could putatively read off from a primal feasible point in SDPB that is not optimized?
Oh, is it, sorry, I didn't ask the question. So I mean,
yeah, I mean, I'm asking some region where one can find a primal solution. It could actually be deep into the allowed region, maybe even. I don't know. There could be some CFT there. Just because it doesn't saturate anything doesn't mean nothing lives there.
Yeah. Actually, I don't know how to extract from, if you just give me a primal feasible point, I don't know if I can extract a solution to crossing symmetry. There should be many solutions to crossing symmetry if you're not at optimality. But if you just give me a primal feasible matrix X, I'm not sure I know how to extract the solution to crossing symmetry from that.
That again concerns the SDP primal, not the polynomial matrix problem primal.
Yes, yeah, so I was basically talking about how big the difference is between the two primal problems.
But it feels natural that if the two problems, if the dual problems are equivalent, that there should be some relation between the primal problems. But I guess it's not so clear. At some point, tried to look at it, and it didn't seem very easy to understand.
I think it's no longer a simple problem. It probably has to do with solving these polynomial equations in some way.
Yeah, it seems that if there's a relation, then it's kind of there's some non-trivial equations. Yeah. Don't want to say anything, but it didn't seem simple. Maybe I'm stupid, but.
So, but Balt, do you recommend to look at your appendix or not?
Let's leave the appendix. I think it's more subtle, but the appendix may provide the first indication. It's an appendix in the n=2 super conformal bootstrap paper.
Okay. Okay.
But I think it's just the first step.
So I'm curious, are there any questions from the students in the audience about any of like these practical steps of like how to make the input, you know, how to run on an SDPB? you know, I just wanted to, I hope this was all clear, because that's, you know, the main purpose of these lectures after all, is to help beginners with the Bootstrap.
Well, I can tell you that I ran your exercise, Docker exercise. Well, I'm not a student, but okay. I ran your Docker exercise for scalar blocks. I hope to run these Docker exercises for this part as well. So
Great. Well, yeah.
I encourage everyone to run it. It was quite simple, actually.
Yeah, I mean, that's the idea, that you can really do everything on a laptop. You know, like you don't have to do any fancy programming for this. It's like, it's a black box.
Actually, I had a question. So I heard that Walter updated SDPB, so it's now it doesn't take a directory, but it takes a file. So is this going? Are your examples still going to run? So or
Yeah,
did he update?
Well, okay. I mean, first of all, you can run different versions of SDPB on Docker. They're all there, so you can just use
Okay.
one. The one I was running in today's lecture was, I think, 2.4.0. I don't. Is that the most updated one, or maybe it's the second most updated one? But yeah, I mean, in any event, if you run the same version I ran, everything should work.
It's not the latest version.
Okay, yeah, okay. So yeah, so I guess maybe I ran the second to latest version, and
But I guess if I use the same version of PVM to input, then so maybe every version comes with its own PVM to input.
yeah. So, yeah, as long as you're consistent with that.
Let me also add for the record that there are other ways of getting, of like preparing an input for SDPB than XML. Like there is JSON and some other things, I think.
Yeah,
and it's a bit, it might be easier to use other methods if people, like, I don't know, use Python or some other things which are not Mathematica, because Mathematica is notoriously bad with all of this, but
yeah,
other
I mean, I would just give you an example.
better.
You know, I mean, I'm a Mathematica user, so you know, I think most people in our field are probably Mathematica users. So like, but yeah, of course, if you're like a more expert programmer and you use Python or anything else, I'm sure there's more efficient ways.
Also, actually, just maybe I missed something, but it seemed that you were creating XML files in Mathematica.
So the output file for Mathematica, what does it look like? Yeah, it's an XML file, and then you run PVM to SDP on the XML file, and then it creates this folder which you then run SDPB on it.
Right. So, like in the olden days of SDPB, there used to be this SDPB.m, which produced XML files and which went directly into SDPB. So that's like you're basically using the same like SDPB.m inside of Mathematica. Right. So I just wanted to point out that instead of using the code from there, I don't know, maybe you made your some custom modifications to this, which would then invalidate my point. But you can also, like, this mathematical objects, which you create like polynomial, like positive matrices prefactor, etc. So you can just output that into just .m file and feed this into one of this PVM to SDP or the other one.
I see what you're saying. So like with the more updated SDPB, you don't even have to do this, I guess, like pre-packaging. You can just like directly put those in.
Yeah. It accepts just .m files.
That's nice to know. I mean, look, in practice, it takes like a split second to do these things, so it's not such a delay. But I mean, perhaps for more complicated bootstraps, that would start becoming an issue, and then indeed this would save some time.
Well, SDPB.m takes a while and more complicated. It used to take a while and more complicated problems. So yeah, just I'm pointing out that you can also don't have to do any processing in Mathematica at all.
Any more questions?
So you're saying, Peter, that there is some format for which tells you how to transform blocks into F functions, into the crossing functions?
No, I'm just saying that, so if you look in Shai's code, then he constructs this, he packages this information into like these things which are called positive matrices prefactor, and there's square brackets, and then some stuff inside of that. And then all this is fed into some function which writes down the XML file. So this function is run in Mathematica. So what I'm saying is instead of sending all this information to this function and waiting for it to run in Mathematica and producing XML file, we can just save the same information into a text file, like export into .m file, and then just feed that like Mathematica formatted .m file into the one of these SDPB helper programs.
Okay.
Instead of like first creating an XML, like this part of Mathematica code is already implemented in one.
Okay, I can read that. Help. Okay, thanks. All right.
Okay, thank you very much, Shai.
Thank you.
Let's. When is your next lecture? I forgot.
Next week at some point. Yeah, so I'll be posting some exercises for this lecture, which will also be a subset of the lectures from the lecture notes online. And then I encourage people to do it over the weekend. This will be the more fun exercise because this is where you actually run SDPB and get some results and see the kink. And so hopefully that should be entertaining.
Perfect. Thank you very much. And see you tomorrow for the next talks.
Bye, everyone.
All right, bye.